Hi,
Awesome.
all. Welcome to Theoretically Podcasting. Today I'm joined by Alex Atanasov yet again. Hi, Alex.
Hey, Vasa, good to see you.
Likewise. And we're gonna dive into random matrix theory and its hop field network applications, ideally.
Yeah,
Um,
yeah, yeah.
so yeah, Alex, you should take it away.
Sick. Okay, cool. I don't think I'll talk anything about hop field networks for today. Maybe in a future podcast we can like apply this to like memory models of memory or also just like general learning algorithms. I might
Okay.
try to apply it to an even simpler model of learning sometime like in the next like hour,
Okay.
which would be probably just linear regression. But yeah, let's
Works
start.
for us. Works
I'm
for
happy
us. Let's
to
do this.
just literally jump right in and sort of uh, talk a little bit about like why I picked this. So even before I start screen sharing, there's like a reason I sort of thought that this would be a fun one for your podcast. Like I think you do quite a bit of random matrix theory, even when you're like focused on more like quantum gravity, string theory aspects. It figures pretty prominently in certainly like our super modern understanding of like 2D quantum gravity in the modern day. And even 20 years back, it like had a very rich intersection with both 2D gravity and basic models of of string theory, of D-branes and matrix theory with a capital M. But it's also applicable in literally every other scientific field that I've like investigated this entire way through. And it's always applicable in pretty like meaningful ways. So yeah,
Very
I'll
cool.
get the screen share going. And let's see if it works. So if I just connect, which might take 15 seconds.
It's all good.
Yeah, perfect. Awesome. So I'm going to be talking about a few various key principles in random matrix theory. It'll almost be like an introduction, sort
Perfect.
of at a really wide audience. So people don't need to come from a physics background even. It's helpful for neuroscientists, computer scientists, applied statisticians. It's even helpful for people that are ultra applied and working like econometrics or something like that. So
Nice.
if there's like two things that appear across all of the modern sciences today, there's probably like two key things, in my opinion, that you cannot escape from if you're doing any sort of even remotely applied science. And those two things will be probability, and the second thing will be linear algebra, aka matrices. And when you combine those two, and you don't often, like usually linear algebra is used to move probabilities around and do inferences and do linear regression on data that comes from some probability distribution. But you could also wonder what happens when the matrices themselves or the high dimensional vectors themselves become random in nature. And you'll see that you kind of create an entire new field of math that's very different from the way you think about probabilistic objects in classical probability. And so their combination is this honestly fairly modern field of random matrix theory. And by fairly modern, I just mean compared to how long probability has been around, since like Reverend Thomas Bayes or whoever, and how long linear
Uh-huh.
algebra has been around. Random matrix theory has only really been like appreciated pretty recently, and I'll call it RMT. And its
Yeah.
origins, like a lot of things, are in physics. So the
In nuclear
original
physics, even.
in nuclear physics, yeah, I think the origin was by Wigner. I don't know the exact year. I think it's like
Me
nine
neither.
something. I want to say it starts either with a four or five.
Yeah, it was when he was alive, for sure.
Right. And he was studying the spectra of heavy nuclei. And I'm thinking it was definitely when he was alive, right? And a heavy nucleus is just like a collection of both protons and neutrons that are very densely clumped together. And there are so many of them, let's say that there are like N of them. There's so many of them that there's no way you could do anything remotely close to an exact diagonalization of the quantum Hamiltonian. you're just hopeless. They didn't even have good computers back then, but I think even with computers now, it's like a meaningfully challenging undertaking.
Definitely, yeah.
So instead of attacking that problem directly analytically, which I'm sure some people at the time definitely did, Wigner and others made an observation that the actual spectra, like what would happen when you look at either the collisions or the
Straight up spectroscopy, even for some
yeah,
reason.
yeah, however you do spectroscopy on nuclei, displayed this really like interesting property that they were spaced almost as if they were random. So
Right.
they looked like they were spaced. It wasn't a perfect lattice structure. It wasn't like super ordered. There was certainly uncertainty, and it varied from atom to atom, from nucleus to nucleus. But there was some sort of like universality to it. They always sort of looked
Right.
qualitatively similar. And the naive thing that they thought is, well, maybe each eigenvalue, right? Because each of these spectra are different eigenvalues. Like this is lambda 1, this is lambda 2, this is maybe ordered in order of increasing lambda. Maybe the spectra are uniformly distributed. So sort of none of them know about each other. Each one lands completely randomly. And so they had what they call like this Poisson model of it, because then it's technically what you would call a Poisson process. Each thing is sort of drawn independently. They don't know about each other. When you do that, you actually get that the clumps are much, much closer together in random places and then sparse in other random places and then together in other places still, and then sparse again. So it's much
Mm-hmm.
more irregular. And the reason it's irregular is when everything doesn't know about everything else, there's no repulsion, there's no attraction. You're just statistically likely to get areas that are clumped and areas that are not clumped. But that's
Right,
not what
right.
was happening here. There was much more spacing between the different nuclei than if it was truly and perfectly
Good.
independent.
So I suppose what you're trying to say is that like if you thought that these were drawn from a Poisson distribution, then you would see a picture like what you've drawn in the bottom left of the three
Right.
that you've
This would
drawn
be
here.
Poisson. Yeah, like Poisson, I'll call it a Poisson process, not to confuse it with the exactly. This would be a
Right.
Poisson process, which you could also just call as like truly random, like uniform. Like
Right.
they're
Right.
uniformly drawn.
So
If it's kind of like the
it's
stars on the night sky, maybe. Like the stars on
yeah,
the night sky
well,
don't care about one another. They're like randomly drawn like this, right? This is different. This is like what we would call hyper uniform. Not only it's I always make a joke that hyper uniform is the type of thing that a human being would draw if you asked them to draw a uniform distribution, because cognitive bias makes you want to separate out the points. And the second you
right.
separate them out, you're actually sort of making them aware of one another and they start repelling one another. I hope it's sort of clear between these two pictures. It's not super obvious, but they sort of know about each other and they don't want to clump up too hard. And so they were noticing this, that the eigenvalues of these random matrices are just super different in nature. They're somehow self-aware. They're random, and there's a universality to that randomness, but it's much more sophisticated than just true randomness.
Yeah, I
That
mean,
makes sense.
we could get the people at home to even run a little experiment where they just scatter
Yeah,
plot what you get by running a random number generator, a uniform
yeah,
random number generator,
yeah,
versus yeah, and just see what it looks like, right?
exactly.
Before you go do the right hand side, which is another thing which you can do,
Exactly.
right? You could totally
And you
do the
could,
experiment.
right, you could simulate the other side, literally draw a matrix. So we'll see.
Exactly.
You'll
Yeah.
see that you can simulate this using the eigenvalues of a truly random matrix, that the eigenvalues of a
Exactly.
truly random matrix repel in a way that just you would not see if everything was sort of not aware of everything else around it. Yeah. Yeah.
So it's
And
like somehow the fact that those random numbers fit together into a matrix will start to matter, right? It's
exactly.
as opposed to just because you can imagine that however many numbers there are in random matrices, well, why couldn't have
Yeah.
I just drawn them all separately, right?
Right.
But the fact that you put them all into a matrix and then you diagonalize, you work out
Right.
what the eigenvalues are, gives you, well, as we'll see, some net repulsion between where
Right.
these objects land up.
Right. And I guess I haven't even motivated. So we already started talking about these random matrices. I think I brought it up a few seconds ago. And So where did we start talking about random matrices when we're just talking about random nuclei at the beginning? Well, Wigner just had a very basic idea that if you had like a vector of all the spins of each individual element of the nucleus, every proton or neutron, and the spins are either up or down. So these are just a bunch of binary variables up or down. Maybe it's a quantum Hamiltonian. The full Hamiltonian will be some sum of the coupling between the spins. And honestly, just thinking about the spins is pretty naive. There's much more to nuclear physics than just the spins. I'm sure there were other variables he was considering. This is sort of a simplified model, but this is sort of the idealized Hamiltonian I could try to think about. Well, let me make sure there we go. This sort of idealized Hamiltonian that you could think about looks exactly like this. And this isn't too different compared to some of the things we talked about last time I was on with the Hopfield model, although this Jij you'll see is meaningfully different. But you do have these sort of like spins sharing nearest neighbor interactions. It's just a two-body interaction. It's a sum of two-body interactions. And I guess you would need to know the details of the Jij in order to actually diagonalize this Hamiltonian numerically. Now, this Jij in nuclear physics is a tremendously complicated object. I'm sure it depends on things about nuclear structure that I've never really studied to full, as much as I could have. But Wigner's ansatz was, instead of trying to figure out the Jij between any pair of nuclear constituents, just make an ansatz that it's maybe just drawn from some normal distribution, maybe of mean zero and some variance sigma.
Mm-hmm.
And ask
meaning that every entry, right? Every entry in Jij is drawn from that distribution.
Exactly. Every single individual Jij is drawn from that distribution. Right, exactly. And you can ask, what do you see then? What is the spectrum of this Hamiltonian? And the spectrum of this Hamiltonian is exactly, you look at J as a matrix, and then you have some set of eigenvalues, lambda I, from I equals 1 to n. You can just ask, what is like the joint spectrum? And what you see universally for any draw of the matrix, and this is kind of amazing, you don't even need to average over different instances of the system. You just take the system to be big enough. And you again see the exact same sort of quasi or hyper uniform distribution of the eigenvalues. Moreover, you get some sort of very interesting plot when you plot the total eigenvalue density, sort of the density of where a given eigenvalue might be on a scale of maybe negative some number k that will depend on sigma and n to positive k. And you see that, if you just had a sum of random variables, so this is what would happen if it was a sum of random variables. You just have a Gaussian. Right? So this is like a Gaussian. This would be for something like a sum of Si from I equals 1 to infinity. Or to n, right? That's
1 to n. Yep.
1 to n, exactly. And Si is maybe equal to plus or minus, 1. Fair enough. That Gaussian will give you that, and it'll range from negative square root n to square root n. That's like roughly the standard deviation of these things. That's not what we see here. So it doesn't look anything like a Gaussian. It's actually much more compact than a Gaussian. It looks like a perfect, already not perfect, a perfect semicircle. Okay, it's really hard to draw a semicircle on that. That's actually
there we go.
A perfect semicircle, whereas meaning like there's vanishingly low probability in n that it's anywhere outside of the semicircle, and it's much more probability that it's somewhere inside here. And this is called the Wigner semicircle.
Yep.
Right. Semicircle law. And it contrasts, and in a very precise sense, the Wigner semicircle is to random matrix theory as the central limit theorem is to classical statistics.
Mm-hmm.
In the sense that, and
for the folks at home, just this is a doable little exercise where you just generate random matrices,
Yeah.
And then do a histogram of their eigenvalues. Just work out what
Exactly.
the
This
eigenvalues are, do a histogram.
is the probability of lambda being equal to this value. So it's lambda on the x-axis here.
And
So
you'll see it.
lambda is exactly the eigenvalues will form this distribution. You can just plot a histogram of the eigenvalues, and we could even do it in Mathematica if we wanted to.
Yeah,
You
or
want
we could
to
just
do it,
put
actually?
up a little collab. Yeah.
Yeah, you could do a collab. Actually, let me try to do let me try to open up Mathematica here. I can stop this share,
Okay.
right? And I think x equals random variate Wigner semicircle distribution. So let me think about that. Is that actually Wigner? Let me see. Wigner matrix. Sorry, not the
Feel
D
like
matrix. Matrix Wigner distribution. Is it? Wait. I'm sorry. What's the Wishart? Wishart is something else. I think I want, yeah, Wigner matrix ensemble.
yeah, I'm not familiar with Mathematica's
Yeah. Oh, it's called the Gaussian orthogonal. So we'll explain this.
aha.
If you draw it from this thing, which is the Gaussian orthogonal matrix distribution, and I think I need to give it a specification of the, so let's say the parameter is 1, the standard deviation is 1, and the size of the matrix is, let's do 100 maybe. So this is standard deviation 1.0, and the matrix size is 100. So X is, if I put it in matrix form, it'll be pretty big. Really big. Okay, great. And if I look at the eigenvalues, so I'll call these the eigs. That's, interesting, just like a random plot. And if I do a histogram of the eigs, okay, let's make a few more bins here. You'll notice it's symmetric around 0. Maybe I'll make a few more.
Well,
Like, let me
yeah, you
do
want to share probably.
40 bins. Oh, did I not? I'm not sharing screen.
No.
That's hilarious. Oh, that's
Okay, here you
I
are.
should have
Okay,
done that
here you
sooner.
are.
Yeah. So let's start that from the beginning. You got to tell me. So yeah, so x is equal to a random variate coming from the Gaussian orthogonal matrix distribution, which we'll talk about a little bit with standard deviation 1, and let's say its size, why not 200, right?
200. Yeah, go high.
So exactly. So x is just this matrix. I can define I as equal to the eigenvalues of x. It's just this list of 200 numbers. If I plot a histogram of the eigs with resolution maybe 20, you already start seeing something that looks a lot like maybe a semicircle. Maybe it's not super convincing to you. But now if I did maybe, let's see how good my computer can do 600. Not too bad. So this is now a 600 by 600 random matrix. And you should think of the random matrix as each entry is basically independently random, but I'm constraining the metrics to be symmetric. So the entries above the diagonal are the same as the entries below the diagonal. Notice how this approaches a semicircle even further. I think when I go to 1,000, which now
Exactly.
takes a little bit longer, let me do a histogram with 100 bins. This almost looks
We already
exactly
see
like
it.
a semicircle. Yeah. So it's pretty cool. And I think I can even show this histogram as well as a plot of the square root of, I think it's going to be something like 50, what was it? 1,000 squared minus x squared. And maybe I don't want to call it, I'll call it lambda squared. This lambda goes from negative square root of 1,000 to square root of 1,000. And I can do another one. Is that right? Square root of 1,000 minus lambda squared? Oh, divided by 2 pi. I think something that 2 pi times possibly 1,000. Let's try that. 2 pi squared root of 1,000. Normalization constant distributions is always the most annoying part.
Yeah.
We may be close. That seems reasonable. Let me just see. Let me just divide the eigenvalues by 1,000 and forget about any normalization.
Yeah, just the 2 pi's.
Yeah. So let's try something like, it might be 4 minus lambda. So we'll try that. Try that. So now it's there. Forget about the 2 pi maybe. Am I forgetting the lambda for some reason? Plot square root of 4 minus lambda. Lambda coming negative 1.1.
Yeah, you probably want to keep it
But it's surprising it's so flat, right? It should not be.
Yeah,
This seems like an
yeah, yeah,
obvious
yeah.
mistake.
There's something funny going on.
Sorry.
Um,
Let's do this. Closer, but
yeah, we see a little bit of a bend.
a little bit of a bend. Always like having to debug this, right? From -2 to 2. Maybe it's actually, let me just throw in an extra 2 pi or something. If we wanted to normalize it, yeah, closer. Pi?
It's getting there. It's getting there.
Definitely getting there, yeah. Lambda from -2 to 2. We're close. I don't know. I don't know if it's worth it, but I think you can see.
But yeah, the idea is certainly there.
My
Yeah. Well,
normalization
no,
was
I
a bit
mean,
off.
but I mean, yeah, for a
For a
little bit
start,
of
it's not bad. Yeah, I can at
simulation
least
on
make
your
it look like a
feet,
more.
it's pretty good. It's pretty
Yeah, I
good.
agree. I agree, and I can at least make it look like a little bit more of a compelling semicircle here.
Uh-huh.
So yeah. So very much a semicircle distribution here happening, and I think at the right resolution, very compelling. So we see this like semicircle distribution in these simulations, which if you get the right normalization constant, you can fit exactly to a circle. And the next thing you can do is sort of ask, what do I mean by a random matrix by this distribution of random matrices? Right. So, and I'll just try to connect to Zoom here to continue. So the question is, I'm defining these random matrices sort of haphazardly, but there should be like a pretty well-defined notion of what it means to draw a matrix. Let's call it maybe X from a distribution. So this is now, I'm going to try to define the Wigner ensemble. So this section will be on the Wigner ensemble.
Right. So
and
just
I
to
should
break
say,
it down, what we're trying to do is go from just having the randomly distributed entries to the X distributed eigenvalues. Like, what is X, right? How are
exactly. So I
how are
want
the
this
eigenvalues
X to be
distributed?
like a random matrix in our n by n. So it's an n by n matrix. But I want to draw this distribution, or I want to draw X from some ensemble, which I'll call Wigner, which is a distribution over n by n matrices with some standard deviation sigma. And what I want is I want X to be symmetric. And I want the expectation value of each entry in X to be 0. Right? So each entry I want to be expectation value 0. But I actually want the variance of each entry, xij, so the variance expectation value of the square in this case, to be equal to some sigma squared. And it'll actually depend on whether I'm on diagonal or off diagonal, but let's forget about that issue for a second. I'm going to stress that I don't necessarily need this distribution. I don't need xij to come from a normal distribution. I do not need this. It is not required.
Sure. Yeah.
You'll actually see that you'll get this semicircle sort of regardless of the distribution of the individual entries, as long as it satisfies this property and it has like a fourth moment that makes sense. In the same way, the central limit theorem will happen regardless of whether the original coin tosses came from a Gaussian or a Bernoulli or whatever. It's just universal. This is the beauty of universality, that you'll see the Wigner distribution emerging regardless. That being said, it is useful to sort of have a well-defined matrix ensemble to come back to. And the ensemble that I'm going to define, the Wigner ensemble, will use sort of Gaussian entries. And the way I'm going to generate a matrix in this ensemble and constrain it to be symmetric is as follows. I'll generate 2 matrices, and I'll call it, I'll generate H, and I will generate it from, this will be Hij, each one is randomly and uniformly drawn from normal distribution of mean 0 and variance sigma squared over 2. Let's do it this way. And now when I look at Hij plus or H plus H transpose,
Mm-hmm.
I'm going to define that to be X. So what properties does
Cool.
this matrix have? So it's automatically symmetric because I've added a matrix
Exactly.
and now we have to ask ourselves, what is the variance of the different entries? And you'll
Yes.
notice that Xij, so what happens if it's off diagonal? If it's off diagonal, then it's a sum of two independent random variables, right? So the variances will just add, right? So the variance for I not equal to j of xij will just be equal to the variance of h plus the variance of, so hij plus hji.
H, yeah.
This will just
H
be
and
the
H
two independent.
transpose two.
Exactly. Hij plus variance of hji, right? By independence, because they're independent. All the entries of H are drawn independently. And this is exactly equal to sigma squared. So the off-diagonal variance is like this. But the variance for I equals j, which I can just write the variance of xii, is equal to the variance of twice hii, right? Which is equal to 4, or sorry, yeah, it's equal to twice. So it's equal to 4 times the variance of h, because the 2 comes outside and gets multiplied by itself. And that becomes then 2 sigma squared.
Right.
So the on-diagonal variance is a little bit different, but this ends up being very helpful. You want the on-diagonal variance to be twice that of the off-diagonal variance. Because then matrix has the very nice property that if you have X and you rotate it to OXO transpose, so you make it undergo rotation, you can show that the off-diagonal variance remains sigma squared and the on-diagonal variance remains 2 sigma squared. And so we say that this is equal in distribution to X. In other words, the probability distribution of these X's, when you pick the on-diagonal variances to be different from the off-diagonal variances in this way, is then rotationally invariant. And I can actually write it in a really clean way. The probability distribution of a given set of Xij, I can write it as proportional to up to a normalizing constant, which, as I have demonstrated from plotting semicircles, I am not good with. The exponential of what we would say, I think it's something like -1 over 4 sigma squared trace of x squared. You can just show that. You can show that, that because each individual entry, I mean, what is this? This is literally just nothing more than a Gaussian in n times n plus 1 over 2 variables, right? And in particular, I think you can see from this that, again, you're overcounting. So there's actually sort of 2 factors of 2 here. There's always a 1 over 2 sigma squared in a Gaussian, but there's also a 1 over 2 because you have to divide for the fact that this trace of x squared double counts both xij and xji, and x is assumed to be symmetric, if that makes sense. So that's what the 1 over 4 sigma squared is doing. And then that'll guarantee that the off-diagonal things have variance sigma squared, and the on-diagonal ones will have variance 2 sigma squared. Does that make sense?
Right.
Cool. Okay, amazing. And now you could ask, so there are some interesting properties about this matrix. For one, the trace of x is equal to 0, right? But the interesting thing is, what is the trace of x squared? So the trace of x squared, well, that would be equal to, well, let's just see. So I have like a matrix of like all zeros and ones, multiplying a matrix of all normally distributed vectors, multiplying a matrix of all normally distributed vectors. Generally, when I multiply 2 normally distributed vectors that have nothing to do with one another, that's fine. That's just going to be 0 off diagonal. So the off diagonals of this matrix product will be 0. The on diagonals will be something different. It looks like every single on diagonal will be something like, and we can do it explicitly, but I think it's something like we're summing, so x squared I, x squared j. Just think about that for a second. So I have like x dot itself, x. So again, what is this thing? The ith entry of this, x squared, semicolon x squared, ith entry is going to be related to a vector of a normally distributed vector dotted into itself. And I claim that for a normally distributed vector dotted into itself, its norm is going as n. Does that make sense?
Yeah.
Yeah. So this will go as n. So the trace of x squared will actually go as n squared because it's going to be n sums of those diagonals. So that's pretty big. And in particular, that means that it explodes as we go to higher and higher n. Higher and higher, right? So that's not necessarily ideal. It would be better if I redefined x by sort of rescaling with n. And for that reason, I will always take sigma squared to be divided by n. So I take sigma squared to sigma squared over n. None of this changes except for adding an extra factor of n here. And then what you get actually is that the trace of x squared goes as n. So, or even I think trace of x squared goes as, actually, no, perfect. Trace of x squared will go as, am I right? Am I just dividing by n? So you'll probably just get, yeah, exactly, it'll go as n. Now you might say, okay, that's still exploding in the thermodynamic limit. But there's a reason that I've just divided by one factor of n. And the reason is that this thing now looks properly like an action. It just has a single n parameter here, like a large n thing that we can do saddle points around. Exactly. And the second thing is that you'll see the sort of invariant correct sort of measure or notion of expectation value that will involve a trace for random matrices will
come with the 1 over n.
Yeah, exactly. There's going to be this central object that we'll see in our theory called tau. And tau is defined as 1 over n times the trace of the expectation value of this random matrix variable. So we're okay with the trace of x squared going as n, but that will then imply the tau of x squared in particular, tau of x squared, which again is equal to 1 over n times the trace of the expectation value of x squared. Well, we've looked at the expectation value of x squared. This will actually be equal to sigma squared on the nose. So this is the tau parameter, and we can motivate it from several different ways. But it'll end up satisfying this very nice factorization
Exactly. So basically what you're trying to say is that if we get n, right, in the numerator, then as we take n to be large, there's a simplification because you see this probability density is basically part of an integration measure. And you're then compelled to do those integrals in a saddle point approximation. And the corrections to those saddle point approximations are going to go as 1 over n or 1 over n to some power. So that's kind of the reason why you do the scaling. And this is the trick that carries all the way into like calculations we do in string theory and gauge theories at large n, whatever. It's the same idea.
Completely consistent, and it's a well-motivated thing across this entire field to do this. And another sort of reason for defining tau to be this way is if you give me, a random matrix X, and I look at tau of X from the perspective of the spectrum of X, what I get is 1 over n trace of the expectation of X. Or again, here X does, I can maybe call this matrix M to differentiate it with this draw from the Wigner ensemble that I just defined. What you get is that this is the same as 1 over n times the sum over all the eigenvalues I of the expectation value of lambda I. And then because you can sort of swap the sum over all the eigenvalues, which are sort of equivalent with this average, you really get that this is measuring in some very precise sense the average spectral thing about this matrix. So that's what tau is really getting for us. It's getting this average idea of the spectrum. And not just that, but if I took any function f of the matrix, let's say I did some deterministic function on the matrix, well, then the exact same argument can apply, and I can just be calculating the expectation value of the function on this matrix. And that's still going to be 1 over n times this sum over the eigenvalues, because that's, the eigenvalues always, you can just...
It's the spectral theorem that you're applying here, basically.
Yeah, it really is basically the spectral theorem. And you see that this tau of the function of the matrix exactly gives me the expected value of f. of lambda on this over all of the matrices, over all the random draws of the matrix, et cetera. Exactly. So this should sort of motivate why tau, which is 1 over n times the trace, is a well-defined thing that you would want tau to be order 1. You would want this
and this is basically what also, you know, we do implicitly in physics when we define the path integral. We put 1 over h bar in front of the action, and we define momenta, right, with an h bar times the derivative.
Exactly. Yeah. You
see,
would
so what ends up happening is that if you, so this is a nice exercise to do, is to try to work out how would you get the canonical commutation relations out of the path integral for, like, you know, one-dimensional quantum mechanics. And if you decide to do this, then you realize that it really matters that you define your momenta in a way that involves an h bar, right, which is inverse of whatever is appearing in front of the action. Right. And then you see, like, okay, you get basically the uncertainty relation. And then if you wanted to, I mean, you could basically also work out you could work out the commutation relations and the uncertainty relation, and you could see that it's in the saddle point approximation of the path integral that you recover classical behavior.
So here you're saying, actually, so under that analogy, so under Vasu's analogy, you're actually saying that you're actually saying here that basically h bar is playing the role of 1 over n.
Exactly.
That's
exactly
what you're sort of saying. And we see
that's
this
what I'm sort of saying here. Exactly. And the point is that that's at the heart of this you know, gauge gravity dualities. There's h bar, someone else's h bar is the 1 over n of the matrices involved. And that's exactly why it works the way it does. So you literally see that the simplicity that arises at large n here is the simplicity that arises from how classicalization involves disregarding fluctuations in these quantities involving tau, right? So you know, if you were to define the variance with respect to tau instead of just the variance as you normally would, you would basically see that there's the property that you're going to get at, this factorization property, which is sort of at the heart of what classicalization is, and why.
I've never thought about it this way. What here are you thinking about as momentum with a thing that has a factor of h bar? Certainly, this looks like a factor.
So it's really implicit in what you. Okay, so here you've defined. So it's the question of how you compute moments of this distribution. So you compute moments of this distribution. There's a trick that you normally do, which is you introduce a source. Right. And then what you want to do is compute derivatives with respect to that source, but not
so
just.
Let's take f of x equals like x to the k, just to be super explicit, right? So if I can like literally then get tau of a to the k is equal to the expectation value of lambda to the k over that matrix. Right? That's what you're saying.
Yeah, well, I'm saying that even if you were just thinking about this in the representation of matrices themselves, right, before we go to the eigenvalues, how I would compute the, you know, these kinds of quantities, right, trace of the expectation value of something, is I would basically introduce into my probability density. So I would write down the characteristic function, or rather I would write down the moment generating function. It's your choice. It doesn't really matter which one you choose. And then you would scale. So you would maintain the scaling with n in that term. So you see, there's an ambiguity. If you just were to introduce, so how would you do, like, how would you compute just expectation values? Well, you just do the regular transformation and introduce the moment generating function with a source, right? But what if your goal was to compute the tau objects from a source?
Right. And let me just like write this out. So let's just say I have some distribution p of x. I can calculate the moment generating function, which is the expectation over x coming from p of x. Let's just call it what? E to the I
exponential
kx? Is that good for you?
E to the I kx. So normally, and now let's say that we just wanted to compute. So this object is I don't know, the exponential of I w of k. Right, that you could write it that way. And then what you would do is you would compute derivatives with respect to k and set k to 0 simultaneously, and that would compute the moment, the nth moment of x.
Exactly. So if I define this, I'll call this z. So if I take the nth derivative of this, I should get something that looks a lot like the expectation value over p of x to the k. That's what you're saying.
Exactly. Now what you would do is you would change. Now if you wanted to get, instead of the x, so this is what you denoted with the bold, the boldface e in the previous in the previous lines. Now if you wanted to get the tau, like tau x to the n, what you would implicitly do is, for every partial with respect to k, you would scale that with, well, you scale that with n, right? Like just like how you scale the momenta, or you scale that with 1 over n. Just like how you scale the momenta with h bar and have 1 over h bar in the action, you scale this with 1 over n.
Oh,
right?
very nice.
So this is kind of like this is, and now that's super important, like in all the stories you normally tell about this, because here we're I'm talking about momenta because it's not a good notion to really make the analogy, because it's not, you need to go to the canonical formalism to make sense of momentum, the operator formalism. But what you really want to talk about is sources for single trace objects. Right. So single trace sources, and
like we usually have something like, in our case, it's going to be something as simple as, again, we're now using random matrices, but there's still going to be a notion of like this moment generating function, which could be e to the I k times like, and maybe it'll actually now be, trace of
trace of x to the something, right? It just depends.
Or something. I don't know what to call the conjugate momentum. This crucially, this is playing the role of momentum.
Exactly.
And I guess what you're saying now, do I need to include an n here? I don't know. I could.
Well, no. So here's the thing. You could do everything by just introducing a source at the level of the matrix itself. But what you're going to have to do is put the trace on the outside of the operation at the end of the day. Because you see, if you just started differentiating with respect to x, you're going to start to break the trace. What you do instead is, it's a bit of a cheat, but you're after something like tau of f of m. So for whatever single trace observable you're interested in, right? Say you're interested in the correlation between trace of x squared and itself. You introduce a separate source. So you introduce sources outside the trace.
So are you saying something like e to the I, maybe some source of like
a trace of x squared?
Right, and you differentiate this. So this would be some sort of, I can define this as some modified z tilde. And I can always differentiate with respect to j of this modified
with the 1 over n, and that would give you the taus, so the tau type correlation.
That's the thing.
Functions.
So I guess what you want to do here is you might want an n times I, ij capital N. So it would be something like I n j tau of x squared, like this, right?
Exactly. So you either do it that way. So either use the expectation value and then you put a 1 over n, or you put the tau and the n in the definition, and then you just do the regular. So if I
differentiate this with respect to nj, I will get something that looks like, I will get something that looks a lot like tau of x squared, right?
Exactly, yeah. So that's the idea. So basically,
and I guess I should be a little careful, because I guess this tau should really be just the trace normalized by n here, because I'm not taking any expectations values in there. Yeah.
Exactly. So that's the essence, right? It's how you, now, I mean, like you could just do it with the regular trace and then put a j, but then be more careful about how you define the taus, right, with the 1 over n. But basically the point is that you're trading off between having the n play the role of 1 over h bar versus the thing like the momentum, which has the h bar d over dx. And that's the point is that like these objects in the large n limit are the things that have an almost classical behavior. They have an exactly classical behavior. That's kind of what you mean in quantum mechanics when you say something's classical.
Right.
So
we can even, without even talking about quantum mechanics, we can even just ask, as n gets larger, we want things to start behaving basically deterministically under these like statistical fluctuations, and you could call that maybe concentration. Or we call this sort of like the saddle point approximation is good in random matrix theory. Exactly.
So that I think is Yeah, it's a fun analogy. It takes us a long way when we're actually doing uh modern day high energy physics. It's
Yeah,
at the
yeah,
heart
yeah,
of
yeah.
a lot of it's at the heart of a lot of
Well,
tricks.
and so basically to summarize the setup now, we have like these xij's, and they're drawn from distributions 0, comma sigma squared that have the 1 over n. So each individual entry goes as 1 over square root of n.
Yes.
But the total, the action or the sort of probability measure, the probability measure on this xij will have something that scales extensively with n. It'll be an exp that scales extensively with n over this 4 sigma
Mm-hmm.
squared times this trace of x squared. And then the final thing that we'll be calculating, these tau of x squareds, will always be O of 1, or rather O of sigma. But the point is it will be n independent under this sort of
Mm-hmm.
parameterization. Just for people that are following along more slowly, this is sort of, all of this is to sort of correctly organize the large n data so that when I take the n going to infinity limit, which is going to be the key limit to study in all of this, this will be the key limit that we care about, things behave reasonably. In particular, this quantity will behave reasonably, even as this gets sharper and sharper. Very cool. Yeah, cool. So I guess what I'd like to do is I've given you this distribution of the individual values of x. And we could ask now, what is the probability distribution of the eigenvalues of x?
Mm-hmm.
Ask what does this look like? What is this distribution? Now,
Yep.
notice that this is the probability distribution in n variables. So I can call this the joint distribution. Because it's jointly, you know, not just about a single eigenvalue, but it's the joint over all the lambda I. But
Absolutely.
I could also sort of integrate over all but one and just ask for a given eigenvalue, knowing everything else about all the eigenvalues and sort of integrating over all of that. What is the density, the eigenvalue density of this thing? So this is truly like the eigenvalue density. Or marginal distribution. And this can also sometimes is often written as rho of lambda. To be super explicit, this p of lambda is equal to the integral over d lambda 1 d lambda n minus 1. And I think this is how Wigner first found the semicircle, was actually doing this explicit integral of
Yeah.
the joint distribution over lambda 1 lambda n minus 1, and then just lambda. So you integrate over all but one. That's the density of eigenvalues. This is the thing that's the semicircle. This is what's going to give you the semicircle. And ideally, time permitting, I'll talk about both this one first and derive it, and then the joint distribution, which you can really derive both of these for the Wigner ensemble and for a lot of other random matrix ensembles. And the name of the game really is to understand the distributions and to understand their moments and to understand
Yes.
how that differs from sort of classical statistics. Yeah.
Yes. Yes.
With respect to these distributions. So the eigenvalues really tell you a lot of things, not just in quantum gravity, but also in machine learning. The eigenvalues teach you how quickly something is learned. The eigenvalue gaps tell you things about generalization, and they also tell you something about the spectral bias of the learning algorithm. In neuroscience, they play similar roles, and
Yeah, we've got to at least hit the linear regression example before,
yeah, we have to
before
at
the end
least
of
hit the
today's
linear regression
discussion.
example. I agree. If we can get to linear regression using all this technology, that would be fantastic. And I will say, it's not just like fun math for the sake of fun math. It really is like a meaningful insight into modern machine learning that people had not appreciated until pretty recently, honestly. And yeah, I mean, I think we'll actually get there. But I think the first thing to tackle is calculating. Let's calculate P of lambda, the joint, or sorry, the marginal distribution. And in order to calculate these spectral densities, and it's very similar actually to what happens in quantum field theory, it'll be very beneficial for me to introduce some machinery. And the machinery that I'm going to introduce is called the resolvent.
Mm-hmm.
Some people will also call it the stilches. Let me be careful. Stilches.
You gotta spell that correct. Yeah, spell that correctly.
Got it, exactly. And all of this is nominally a lot like a free field propagator.
Yes.
And what is it? For a given matrix, let's say I have a random matrix A. Let's say it's n by n, real and symmetric, just to make it as ordinary as possible. I define its resolvent, G of A, to be a function of Z. And that is given by 1 over Z minus A. Or equivalently, if you want to be really like rigorous and not abuse notation, it's the identity times Z minus A as a matrix inverse. Does that make sense? So in terms of the eigenvalue, so let's ask a very basic question. What if I just did 1 over n times the trace of G, just like what we were doing before, GA? Well, I can always express this as, in terms of eigenvalues, as the sum of 1 over n times the sum over I equals 1 to n of 1 over Z minus lambda I. So this thing has poles at each lambda. That's interesting. But then you might ask, okay, so now let's take n to infinity.
Mm-hmm.
And one of the things you'll see for these matrices is, although for any given fixed n realization, you'll have, maybe this is the real axis and you'll have a bunch of eigenvalues here. For a given realization, maybe for a different realization, you'll have like a bunch of eigenvalues also in that general range, and you will see that they're sort of distributed in this hyper-uniform way. Once you take the n to infinity limit, these eigenvalues start clumping up, and you see this super
They form a cut
that looks like a branch cut of very specific supports, at least for the Wigner matrices that we're going to work with, on the real axis alone. And you can study this as a function of complex Z. For Z off the real axis, it's pretty obvious that this isn't going to have poles because all the eigenvalues are real. And this is actually a really informative thing. One of the ways that's obviously informative is this already contains all the moment information you could ever want. Why does it contain all the moment information that you could ever want? Because around infinity, which as we see here is actually a holomorphic point, we can just expand this G of Z. And we can expand, I'll define this 1 over n trace. I'll define this with a lowercase G of Z. So I think, strictly speaking, I think the Stilches transform is actually the lowercase version of it. And you can see that G of Z, ooh, my pen is malfunctioning a little bit. G of Z can be turned into a series in n of 1 over Z to the, I think it's n plus 1. And then it's just tau of A to the n. So you automatically get, exactly. And it's as simple as that. I think there's also you can get negative moments. So if around lambda equals 0 or around Z equals 0, G is analytic, which in this case it's not. But it's sort of the idea that maybe there's a gap and the lowest eigenvalue is not at 0, but maybe some meaningful distance above 0. You can meaningfully calculate negative moments, and you can see that G of Z is then equal to the sum over n of this holomorphic Taylor series, Z to the n, and I think it's tau of A to the negative n minus 1, something like that. So the n equals, I think, 0 to infinity, maybe with a minus sign here. And this is n equals 0 to infinity in both cases. So in both cases, you get not just moment information, but moment information on both sides if you can do the expansion. It's a very statistically useful quantity. Were you going to say something about Sue?
Yeah. So this again takes us back to like what we can do in physics. So first of all, this is like, well, okay, so who is this the propagator for? Well, it's a propagator for the system whose Hamiltonian is given by A.
Yeah.
right? And so you can see that basically you get
The
these
propagator in
formulae.
quantum mechanics.
Exactly. It's as if you took the quantum mechanical propagator for a system with the Hamiltonian A. And then you basically see that the reason why you get the behavior that you just described, right? I mean, if you well, actually, if you did this carefully, you would realize is actually okay. You should really be using little g of z again with the h bar and the normalization and everything, and you see that basically these are the kinds of tricks you would use to segue between, well, okay, so in the proper time representation, right? This is basically the way you would segue between what information the propagator has and what information, say something like the heat kernel has versus what information the partition function has. And so that's a really neat exercise. And the second thing is that this phenomenon of the poles condensing into cuts is exactly what happens in the semi-classical limit of a quantum mechanical system, because you can define the momentum. So we just discussed how we think about the momentum, right? If you think about it in the position representation as the derivative, well, you take the derivative of the logarithm of the wave function, say, right? That thing is a stand-in for what will one day become the classical momentum. Okay, so this is like
logarithm of the wave function here.
Exactly, because you see, you want to take it's kind of like you want to take the wave function over to the other side, right? Because you just want the momentum. You don't want the momentum acting on something, right? In the semi-classical limit.
I see.
And in exactly this fashion, what ends up happening is that as you approach h bar equals 0, the poles, right, are going to condense into a cut. And you're going to basically discover that this thing, the logarithm of the wave function, is playing the role of Hamilton's principal functional, right, in Hamilton-Jacobi theory, right? And you see that thing has in a very simple mechanical system, it has this square root structure. So of course it's going to have a branch cut. And you you can sort of see this in action. This was brought to me, at least, by courtesy of course by Pedro Vieira about
really?
about it's one of the Perimeter Scholars International no, it was advanced string theory, ironically. It was about the integrability in ADS-CFT
that
story.
actually makes a lot of sense for papers.
But I mean, the fact is an elementary quantum mechanical fact. So
it comes directly out of I mean, basic quantum mechanics. And honestly, it's just funny that we discovered things in this order, because really, I mean, really quantum mechanics is making use of this like sort of basic mathematical principle about, well, I don't know. It depends on how you think about it. Does physics come first?
No, I agree.
I don't know. Because that's a lot of my hot takes on a lot of like aspects of holography that seem to like apply to other fields of science, is that holography is seeing random matrix theory in a very deep and profound way. And I think that matrix theory in a very deep and profound way affects other aspects of the sciences too. And it's kind of interesting that we discover so much about these universal structures by asking for sort of physical questions about gauge theory and gravity and all of this. Or even quantum.
Indeed.
So I'll continue this sort of train of thought. We introduced this thing. What is it really good for? Well, I think we've made an argument that it's actually kind of good for a lot, and not just that, but sort of in, you could really for an infinite n matrix, this thing still makes sense. And the way that it still makes sense is this g of z is equal to sort of this 1 over n times the sum of a Dirac delta every eigenvalue divided by or actually, sorry, so what I mean is, so it's equal to not a sum anymore. I'm exchanging the sum to an integral over d lambda of lambda minus lambda I. There we go. This is what I mean. So the 1 over n will go directly to the integral now. And now I'm going to have a lambda minus lambda I. And I guess I'll still be summing over, actually, let me be a little bit careful. So let me do it in two steps. So first, let's do the finite element case. So as we were just describing, this is the finite element case. Whatever, it's the sum of 1 over z minus lambda I. But this could also equivalently, so this is the sum over I. This could equivalently be viewed as a sort of integral, or rather, right, an integral from negative infinity to infinity of the density of eigenvalues lambda over z minus lambda d lambda, when rho is equal to that empirical sum, I equals 1 to n of the delta functions of lambda minus lambda I, if that makes sense. But
with the 1 over n here, yeah.
Yeah, with and that's really important. Yeah, so this rho has to be normalizable to 1. So here rho of lambda is just equal to this 1 over n. The point is,
and so here you've done nothing special. You've just rewritten the sum in terms of delta functions in an integral. Yeah.
Nothing special, but this thing now makes sense when n goes to infinity. And when that sum of Dirac delta functions turns into this cut. And this is the real Stiltsches transform. So this is Stiltsches is exactly this integral transform right here. And one of the nice things about the Stiltsches transform is, knowing this fact, I can just evaluate g of lambda. So now I'll actually take lambda on the cut. So lambda here is in the cut. So g of lambda does not make sense. It's like a ill-defined thing. It's infinite. I have to pick a side of the branch. If I pick g of lambda, and if I'm not mistaken, I think it's actually lambda minus I epsilon. I'm always confused with the I epsilons. It is minus I epsilon, the I epsilon prescription, just like in quantum field theory. This gives me something kind of interesting, and anyone that can recognize sort of these I epsilon prescriptions know that when I go to lambda minus I epsilon, this 1 over z minus lambda becomes increasingly more and more like a delta function, and I can recover from the imaginary part of this.
Yes.
Something that looks like pi times the density of rho.
Exactly. So basically, we can break this down. So you write the delta function in terms of its principal value definition, right? And the principal value definition is that it's the difference of two rational functions, which have one comes with a plus I epsilon, the other comes with a minus I epsilon, right? So the delta of z is 1 over z plus I epsilon, and the other is a z minus I epsilon. And then what you want to say is that actually, if I thought about this in terms of, just in terms of complex values, that's just defining the imaginary part of the 1 over z minus epsilon, the I epsilon thing, right? So that's the principal value definition of the delta function. And so you just use that at this level formal manipulation and turn that into a definition of what you mean, right, by the density when you take n to infinity.
Exactly.
Because you don't actually know what that is. Yeah.
And in that last step, I just want to stress that this equation is just like a true thing for any sort of epsilon, is when you look at this, you're really just replacing this with this epsilon over z minus lambda squared plus epsilon squared. It's a very simple manipulation. But as you take epsilon to 0, this actually approaches pi times the delta function of z minus lambda. You can get this exactly from doing contour integrals. So this is basic contour integration. You do a half contour around the pole, and you can get that. You'll get a delta function exactly when z is equal to lambda with an extra factor of pi that's coming from that half contour. And this is like the main thing, the main reason. This is what we would call this is the inverse Stiltsches in some sense. So and not just in some sense, it's literally inverse. So it's very different than like Fourier and inverse Fourier. It's sort of a much more clever, complex analysis goes into this. But all this is to say that this is secretly repackaging the eigenvalue data exactly. You give me the distribution, I can give you this resolvent. You give me the resolvent, I can give you the distribution. So spectral statistics, or resonances, or whatever you want to call it, the spectrum of this matrix is repackaged very neatly in this propagator. And I'm sure there's like a very nice you have T
And
interpretation.
that's as it is for sure in physics. I mean, like if you think about
Yeah,
what you do on a lattice in a lattice simulation to talk about the spectrum of
yeah,
a theory, well, you're just gonna go compute the full the non-perturbative 2-point function. That will tell you where all the particles are, where all the excitations
exactly.
are, right? Whether they're
That's a
glue
great way to
balls
say
or
it.
whatever.
The excitation spectrum, the spectrum of all the particles, both bound and free, is captured in that propagator.
Exactly.
Um, and
Exactly.
giving that gives you the spectral statistics of the quantum field theory as well. Same thing for random matrices. And again, you know, the random matrix theory was there even before you go into quantum field theory and like n dimensions, or it's just like a universal
Right.
truth about eigenvalues of these really simple matrices. So the name of the game is now to just calculate this G. And there is
Yes.
a pretty quick way to calculate it. And there are several ways to calculate G. So calculate this G, calculate this Gx of Z. For X of X is, again, coming from a Wigner distribution
Mm-hmm.
of variance sigma, n by n, whatever. There are a few ways to do it. I'll just enumerate the most sort of popular in the mainstream, world is the replica theoretic method, and we might get back and redo it using replica theory.
Mm-hmm.
That's sort of like the real machinery. That's the real heavy lifting. It's the part that, the first time anyone does replica theory for a problem, it's usually not rigorous on mathematical grounds, and we'll talk about what replica theory even means, time permitting, or maybe in a different episode we can go in much more detail about replica theory. But I actually want to do something that's even simpler, that you don't need to use any analytic continuation or unstable mathematics to get to, and
Mm-hmm.
that's called the cavity method. I should not call this, maybe I'll just call it the replica method, not replica theory. These are two methods. There are other methods too. And then actually we'll talk about, there are methods that you can first get the joint distribution and then marginalize. That's what Wigner did. But I'm just going to focus on this for the next 15 minutes to get
Mm-hmm.
this exact same result using the cavity method. And what is the cavity method? The cavity method is a version of, I guess, mathematical induction, really, where you consider the n by n system and try to relate it to the n minus 1 by n minus 1 system. And the way we're going to do that is I'm going to denote by G capital N the resolvent of n by n matrix. And I'm going to denote by G n minus 1 the resolvent of an n minus 1 by an n minus 1 matrix. And as n approaches infinity, these should be the same because the resolvent has this nice property that, as we saw, the density is actually concentrating to a fixed thing. And we can even show this in rigorous terms that actually independent of the matrix you're drawing, as long as it's big enough, it's actually going to give you the exact same density. We saw that the density gives a unique resolvent. So you'll get a unique resolvent, and in particular, it should be independent as n is super large, whether it's n or n minus 1. You get like a real equality. Maybe I'll, just because at finite n this is never true, you'll get this to become increasingly true, increasingly true, increasingly true. Maybe you can say that Gn minus 1 is approaching Gn, whatever. I'll do it what I had before. Okay, so how can we calculate this? There's a crucial trick that is always applied in these like statistical physics of disordered systems thing, especially when you use random matrix theory. And physicists don't see this trick very often. And the key trick is something called the Schur complement. And this is what that means. So let's say, again, I have that x, which is my Wishart. The thing I want to calculate is z times the identity minus x. That's just a matrix M. That's the matrix. This is a super easy matrix to calculate because there's no inversion, there's nothing. The difficulty is I want to calculate G, and that's equal to M inverse. This is, again, n by n matrices. These are n by n matrices. Well, if I look, there's something very interesting if I look at G. And again, this is n by n, but there's like sort of a 1 by 1 corner here, which I'll call G11. And then there's a bunch of stuff here, and there's a bunch of stuff here, and there's a bunch of stuff here, right? And I could ask myself, what is this upper top right corner G1? Because you can imagine this, like, is this bottom part is a little bit like the n-1 system. And I'm sort of adding that top left corner, the G11. And I could just ask, what is that in terms of quantities that I already know? But what G11 is, by the way, I want to stress, this is like a scalar. There's nothing, even though it's a capital letter, it's the 1 component. That scalar is in any matrix inversion, you can exactly write as G11 is the inverse of this quantity S, and S is called the Schur complement of M. And what is the Schur complement? Well, I can just write S. It's a pretty, like, and this is just a very basic identity in matrix inversion that they teach you in any, maybe not linear algebra course, but numerical linear algebra or like computer science course where you actually have to invert matrices. It's just M11 minus the sum over both K and L of M1K, that is, the bottom, the top sort of row of M, not including, this is ranging from 2 to N, times M22 inverse. So that's M22 is like everything else times ML1. This is maybe like the most math heavy equation I've written so far. I just want to stress that what is M11? Here's M again. Here's the matrix M. This is M11. This is M22 right here. That's an actual matrix. So again, M11 is just a scalar. This is M1K. And this is ML1. So this is M, I think KL is equal to this matrix here. Does that make sense? Hopefully people can see that. So now all I want to do, let's first just try to calculate something about, I want to just know something about the expectation value of S. Because the nice thing is, okay, there is still this inverse. I still have the problem of inverting a matrix. But now I have the problem of inverting an n-1 by n-1 matrix. So maybe some fun induction thing will happen to save it, right? I want to look at the expectation value over when X is drawn from my Wigner distribution of this Schur complement thing, because that could maybe help me. Then I'd have to do the inverse. Now you might argue that, wait a second, you're going to invert something. So what you really want is the expectation value of the inverse, not the inverse of their expectation value. But we're about to see that that's actually going to be okay, because I'm going to be inverting something that has very nice statistical properties, which is like the diagonals of this G matrix. Let's first just, in an exploratory way, see if we can massage this in any capacity. Well, right away, the expectation value, what's the expectation value of M11? Well, M11, how did we define M11? M11 is just equal to Z minus X11. X11 is just a random variable over X.
Right.
So this whole thing is just the number Z. That's a great simplification. And then it's minus, and then we have this sum, and we can safely take the expectation within that sum. Again, that sum of K equals 2 to N. And then what do? Well, we have this expectation value, but the nice thing is that this M1K is actually completely independent of the M22. And why is that true? Because the M22 inverse is that completely different subblock. And then we have, so we do have this M22 inverse, we have this ML1, and this is the sum over X. Now, again, these things are literally just negative X, because there's no, these are off diagonal things. These just look like negative X. This is the negative XL1, this is negative X1K.
Yes.
And so you'll get something. So what do I know about the expectation value of X1K and XL1? Well, I know that that's just 0 unless K is equal to L. Why do I know that? Because X is symmetric, so these things are the same variable when L is equal to K, but not when it's not. When it's not, because they're independent of this guy here, it'll just vanish to 0. So I can rewrite this guy as equal to Z minus the sum. And actually, I can maybe simplify even more. When they're equal, they're just equal to sigma squared, because they're off-diagonal components. They're just equal to sigma squared over n. That's their variance. And then I'm just tracing this M22 inverse guy. Right? Does that make sense?
Yeah.
That's very nice. That's actually really clean, because there's something really nice. I'll massage this in a maybe more suggestive way. Sigma squared times 1 over n times the trace of this guy. Right? Well, but this is just, okay, first two things. one, we should immediately recognize that like this is tau, right? Like this is just
That's tau
tau
of
of M22 inverse. But what was M22 inverse? First of all, M22 inverse is just the n by n minus 1 by
n
n
minus
minus
1.
1. So this is actually exactly the definition of lowercase g. Remember, lowercase g is tau of bigger g. G n minus 1 of z, basically. So this whole thing is just z minus like that, right? So that's my sure complement. That's a pretty nice expression. And now there's a really important point. There's a really important point here. So this G11 number, this scalar will tend to a deterministic number with negligible fluctuations. And let's kind of like explore why that's true. Negligible fluctuations. Let me just first say it that could be true. And if that is true, then something kind of beautiful happens, which is that G11, which we just said was S inverse, the expectation value, I can just safely write the expectation value of G11 is equal to the inverse of the expectation value of S. I can just commute the expectation value with the inversion. And as soon as I do that, I all of a sudden get, well, G11 is just the 1/1 component of that matrix G, right? Which is just by sort of permutation and variance along the diagonal. This is just equal to 1 over n times the trace of Gn. So this is just already what we were looking for. So this is exactly tau of Gn. And then this we just showed was equal to the inverse of the following, z minus sorry, it's not even tau, it's just lowercase g at then, is z minus sigma squared Gn minus 1 of z. At finite m, there's a meaningful distinction between
inverse,
the two.
Probably, right?
Inverse. Yeah, exactly. Inverse.
Yeah.
But as n goes to infinity, this doesn't matter.
Yes, and that's...
And this becomes just a quadratic equation. You can multiply both sides.
Self-consistent equation, yeah.
It's a self-consistent equation, exactly. And immediately from this, you actually get something pretty direct. You solve this self-consistent equation. It's just a quadratic. You get g equals z plus or minus. And the plus or minus can be chosen by ensuring that the cut is in the right place. And it'll turn out that you need to actually pick minus. One, I think it's like, to be super clear, it's, if I wanted to be super clear with how I'm doing my branch cuts, it's z1 minus 4 sigma squared over z. This way, when z is small, over z squared. This way, when z is small, you're guaranteed that the thing in the denominator is negative and you get a cut. All over 2 sigma squared. There are other ways to like write this, this square root, but this is the most explicit. So this actually gives you the exact form of g. And from this exact form of g, you can even see it already at this level. It's z is out front and there's a minus 4 sigma squared. When you actually take the cut and you take the imaginary part, you immediately get an implication that rho of lambda is equal to, I think something like 1 over 2 sigma squared times, I think there might be a pi. Yeah, there's a pi, by the way, right? Because I have to take the imaginary part and that gives me pi rho, so I have to divide by pi. And then it's the square root of, and then I flip the thing inside the square root because I'm taking the imaginary part.
Because you want the imaginary part, yeah.
And this is like the central equation. This is sort of the answer right here. We got
that's the semicircle. Hell yeah.
Hell yeah. Yeah,
we got it with the thing that you were trying to plot.
Yeah, we got it with the actual thing that I was missing before. So I've actually
you derived the answer to your problem.
Yeah, the answer to my original, right, exactly. So if n was like my 1000 thing, I'm gonna actually rerun it in a second just to see, because I really want to actually get the correct square root scaling now.
Yeah, this also, I mean, just in physics is very reminiscent. Well, not the logic, but the end result is very reminiscent of the things like the gap equation, which you have in the large n limit of a vector model. You have some very similar. The gap equation. It's a clever way to deduce the large n limit of the non-perturbative 2-point function in a vector model. So,
Oh,
well,
interesting.
usually you do this in the sigma model, like a nonlinear sigma model with like a compact target space. And then what you're going to try and do is deduce the exact 2-point function of, I think, the Lagrange multiplier field. And then you sort of, yeah, you get a gap equation that just lets you do it. So the way you solve the model in a sort of old-fashioned in the old-fashioned way of just getting the solution to the vector model at large
Yes.
n is through this gap equation.
Oh,
So
interesting.
you obtain some non-perturbative 2-point function. That's like everything. As we know,
Oh,
like a non-perturbative 2-point function is everything. So
yeah. I mean that makes sense. The entire spectrum. Exactly.
yeah. So I mean it's the way you get to the end is a little bit different, but like the end result looks very similar. So,
Wow. And also speaking of which, now that I actually have the correct normalization constant, I'll stop this share for a second just so I can show my main screen.
yeah. You should.
Here's the exact. Now I have the exact formula. I know. I get it.
You get
Ironically,
it.
this was actually already correct. I had just forgotten to specify that the histogram should be a probability density function. Once you do that, you
Yeah.
get, I mean, this perfect semicircle. Now let's make n maybe like
Nice.
3,000. And it just gets better and better, I think. Just like super clean. I mean, that's amazing agreement. You can even see fluctuations outside of that range are just like very small.
And in contrast, if you were to plot the histogram of just random, like uniform or whatever, just normally distributed it's like numbers, you're gonna see
Oh
sort
yeah.
of Gaussian that looks
Yeah. I mean, you get
quite
something much
unlike
more like,
this.
yeah. I mean, I could even maybe just for the sake of showing a plot, 1/2 square root of 2 pi. The Gaussian looks super different. And in statistics jargon, it's platykurtic. It's what you would call and let's make lambda go from -3 to 3. Does that do it? Yeah, perfect. So, and maybe I can do I don't remember how to change colors because I've been so Mathematica or Python matplotlib.
Yeah, you're ahead
Yeah.
of me. You're ahead of me in remembering how to do these things in Mathematica.
Yeah. I mean, I totally, yeah. I mean, I'm not
I've
by
forgotten
no means am I like actually good, but you can just see that it's super different in terms of just everything. Like
exactly.
one of
Very
these is
good,
like
very good. This is
normal
perfect.
distribution, exactly, just very different. Platykurtic means that its tails are much less fat actually than the normal distribution. And
Which
I'd
is
actually like to
weird.
give you a sort of intuition for why that happens. Because there's a very beautiful reason that happens in terms of what, again, in random matrix theory we would call free probabilities. I guess in physics you'd say the diagrams that cross don't contribute. And actually you can if you just looked at like, the 4-point function of a free field, if it was just a scalar free field, you have 3 contributions from all different organizations of those 4-point diagrams. But for a random matrix, one of those diagrams dies. And I can maybe just make a quick comment about that. So there's one thing I didn't justify, but actually it kind of is justified. The one thing I didn't justify is just that that G11, the scalar in that matrix sort of concentrates. The idea that like this matrix, like the diagonal entries all sort of go and tend to this G value. And I'd like to think of like a simple way that I can argue that. One of the simple ways that I could argue that is it's a good question. I'm trying to think of maybe a quick argument. Maybe I should mention the book that I'm working out of, and that's actually very important.
Okay.
YouTube description, you should definitely have it because I mean a lot of this good stuff is out of this book. So the book
Hell
that
yeah.
I'm
Okay.
using that I use to derive all of this is from a first course in random matrix theory. And it's by 2 really prolific scientists in the field, by Mark Potters and Jean-Philippe Bouchard, I think is the way you would pronounce his name. Bouchard. So this is a great book. I've worked through a good chunk of it, and it really like meshes the physics intuitions with the more data science, machine learning intuitions, and it really gives you a lot of these things. Yeah. I guess one of the things that I would just mention is that yeah, this main matrix, this G11 term, will really be related to the fact that because the main matrix really tends to this, like, I guess what I could say is basically that because the differences between the successive matrices are negligible, you can make a good argument that this G11 term will really concentrate pretty sharply. And I guess I kind of don't want to go too much into detail there because I think physicists will believe you right away. This G11, like the whole G matrix concentrates on its diagonals. It becomes zero off diagonal, and it becomes very close to lowercase g on the diagonals, right? So a rough sketch is just this propagator G basically looks like lowercase g times the identity. Yeah, something like that. We can verify that the tau on both sides gives G of Z. Tau of the identity is 1. That's another reason why we like tau. Yeah, and I guess I can make a quick comment here. Like we derive the resolvent using these cavity methods. There are other ways that you can derive it using diagrammatics. Like you could actually try to get a formula for all orders of the correlation functions. You could consider just like, there are actually just formulas to calculate tau of x to the k for any number k. And you'll find that for k equals odd, this is 0. And for k is equal to even, naively you might think this isn't too different from a Wick contraction. This theory is fundamentally free in a lot of ways. And you're almost right. And I'm not going to prove why this happens, but you can show this pretty directly, and I will at least give intuition. Let's look at, like, okay, the simplest one is a 2-point function. That's trivial. We already calculated tau of x squared. That's sigma squared, right? What would the next non-trivial one be? It would be tau of x to the 4th. And the way you calculate this stuff, I mean, you are still doing Gaussian averages, so everything would tell you that Wick's theorem should work when you calculate this tau. And Wick's theorem does work. But keep in mind, this tau isn't just an expectation value. It's an expectation value that's traced and divided by n. Yes. And what that gives you is that there are, again, 3 diagrams. There's this diagram, and then there's this diagram. And it's just showing you the different ways you can connect them. Both of those diagrams contribute as normal. And so when you sum both of those diagrams, you'll get a 2 sigma squared. But in classical free field theory, there's a 3rd diagram that you need to consider. And it's this diagram. Let me make a good color for it. It's this diagram. This sort of loops under. And the difference between the first 2 diagrams that I just drew and this other diagram is that the contraction, the trace is aware of the ordering of the matrices. It's not like in CFT where you can just move them around in any high dimension and put them in any order you want. The trace really gives an ordering. It's sort of like, think of the trace.
This one's not planar. That's the issue, right? It's not planar. That's true.
In some fun, it basically is not planar. I sometimes hesitate because you could always be like, oh, well, what if I drew it underneath? Then it would be planar technically. But like, you should always think of this as going, maybe you should actually think of this as like truly cutting a hole out of the Riemann surface, like this trace or something. And then it really isn't planar. There's like no way. It's sort of a no man's land to go within the loop of the trace. You have to go outside of it. It's non-planar. So for most physicists, the second you say non-planar, it's like, okay, done. There's no reason to think any further. It's going to be 0. There is actually a way now in terms of like this very modern approach to random matrix theory called free probability to explain what's happening. So there's an obvious reason why this is not going to give 0. It's because this matrix is right next to itself and it's about to get contracted into itself. And we already saw that when you contract a matrix into itself, the diagonals start concentrating to these things that look like sigma squared. And that's going to happen twice. And sorry, this is actually going to be sigma to the 4th. Right? Because it's going to happen, it's 2 copies of the sigma squared matrix. Those 2 copies are kind of like independent and they won't talk, well, there's no contraction between those 2 copies, so they'll just sort of each contribute sigma squared. But here, what's going to happen is you're going to contract this dude with his friend. But in doing that contraction, you have to pass through another copy. And the crucial thing is that at this point, so maybe this is insertion X1, and this is insertion X2, or this is insertion X3. The crucial point is X2 is randomly oriented with respect to X1 and X3. In other words, you can actually always pick a basis that X1 is diagonal, and then X3 is just some other thing that you would want to contract it with. But this second guy introduces a random reorientation. And whenever you're in high N and high dimensions, a random rotation will completely kill off any correlations between those matrices. So in a very precise sense, X2 looks like OX1, O transpose, where O is a random rotation, random orthogonal rotation. And that completely kills off the correlations. And one of the consequences is that means that tau of x to the fourth is equal to 2 sigma to the fourth, which is not equal to 3 sigma to the fourth. That automatically implies that the tails are lighter.
Yes.
Tails are lighter. And that's exactly what we saw. That implies that we get a semicircle, not a Gaussian. If that makes sense. And so this is really, you can show that sums of all these random matrices, when they come together, will always come together to form this Wigner distribution, and not anything else, not a normal distribution, because of this fundamental like free probability rule. So I've talked a lot about this stuff, and I'm trying to decide whether it's worth just making a comment on how you can take this idea and apply it to linear.
Let's do that.
Yeah,
let's do massively over parameterized linear regression.
Because I honestly have as much time as you want, Ross. So I don't know how.
Let's go.
Like
let's just go.
So let's do it.
I mean,
okay, so,
YouTube's gonna have to deal with it.
Yeah, exactly.
That's what I think.
Exactly. Beautiful. Love it. Okay, fantastic. So this is also, I'm going to try to aim for not like hardcore math, but just something intuitive. So, so this is going to be a completely different distribution. So this is now what we'll call the Wishart distribution. And just like we motivated the Wigner distribution by analogy to a Gaussian. So what Wigner was to the Gaussian, so will the Wishart be to the chi-squared. And you might say, oh, the chi-squared distribution, that's kind of like a random distribution to care about. Like, why would you care so much about the chi-squared distribution? Well, chi-squared in statistics is very important because it measures variance. The variance, the empirical variance that you estimate by summing up, this is always the sum of a bunch of xi squared, where each xi comes from a normal distribution. That's what a chi-squared looks like. A Wishart then corresponds to a contraction of, and I want to do this in the right sort of statistical. So I basically take this X matrix, and this X matrix is not a Wigner matrix like before, but rather, and I'm just trying to decide just to be consistent with everyone's notation, maybe just so that we don't confuse X with the X's we were doing before, let's call this instead H matrix. And this H is crucially like a non-square matrix. And the dimensions of H are what I'll call N by, let me think of a good number for, I guess if I was a classical statistician, I could call it, let's call it T. This is what they'd call it in that book anyway. And here's how you should think about it. N is your number of data points. Data points. T is equal to the dimension of the observations.
Okay.
So this is literally like linear regression is exactly this. So H is literally your X matrix that you feed into linear regression, right? So
Yes.
usually H is n by t, then your y, so H is kind of playing the role of your x's in linear regression. In linear regression. Maybe I should call it x, but let's just call it h. H is just the variables I give you. Y is the response. And if y was exactly linear at h, it would be h dot beta. Because then, again, beta is contracting over the actual dimensions that the variables are living in, and then this is an Rn, which is exactly equal to the number of your observations, right? And linear regression is done this way. Okay, so now I could actually calculate something that's called the empirical covariance. So usually H, the entries are drawn, like the Hij's, are drawn from a normal distribution in high dimensions with a covariance C. And C is just in R T by T. T, again, is the observation space. T by T sort of defines this Gaussian distribution on the actual space that I'm drawing.
And the reason you're saying this is that if we have, I mean, this is, well,
yeah,
you can have all sorts of situations where this is not the case, right? I mean, the data is what the data is. But what you're saying is that we're modeling the data by some, I mean, by some Gaussian through some, you have some CLT logic going in somewhere in the middle here, right?
Yeah, that's a great point. There is a little bit of a CLT logic here because you, and not even CLT, but actually a completely different thing called like the Gaussian universality principle. And the point is like, at the end of the day, I'm actually going to be taking n to infinity and t to infinity at the same time. But I'm going to cap n over t fixed. I'll call that a parameter. And I don't know, I guess like in this book, the parameter is called q. I'm trying to.
Do you want that to be smaller or larger than 1? What do you want it to be?
Exactly. So whether it's smaller than 1 or larger than 1 will exactly determine what domain in statistics I'm in. So Q,
makes sense.
Number of observations relative to the, so Q is greater than 1. That's classical statistics. That's also underparameterized. So a little, it's sort of the opposite of like the other parameters. Sometimes people use alpha for the reciprocal of Q. So this is underparameterized. And that's classical statistics. And like, we kind of know what happens there. When Q is less than 1, that's the new like modern overparameterized regime. And now you might say, that's all well and good. Let me turn on the lights just for a little bit more visibility. You might say, that's all well and good, but what is, why are we modeling these things as Gaussians? Why are we modeling the supervised signal as linear? It's a very fat assumption that's not realistic. It's not fully realistic compared to what people do in deep learning, but there is actually a realism in it when the dimensions grow higher and higher. And the reasons for that is that your true generating process can be very accurately modeled by a Gaussian or a mixture of Gaussians when the input dimension is very large. And that's just because you would need a tremendous amount of data, more data even than in a lot of like modern deep learning things, well, or at least moderate scale deep learning experiments, to be able to distinguish a Gaussian source from a source with higher order moments. So actually this Gaussian assumption is very reasonable under the assumption that your data is scaling with your input dimension. Yeah. In some sense, there's actually no other regime you can be in. Yeah, the amount of data you're receiving is scaling with the input dimension. That's exactly what this means.
I see. Well, I see what you're saying. Yeah.
And this is your data set size. Yeah. They're scaling together. You can't, as long as you have this joint linear scaling, you can't distinguish much more than a Gaussian. Now, if your data set was scaling quadratically in your input dimension, you're in a completely different regime. Then things actually do matter. You can't just be assuming Gaussians all the time. But think about something like CFAR. CFAR's input dimension is 700 or maybe 1,024. So up until you have 1,024 data points, the Gaussian assumption works. There is then a breakdown of it, and that does deserve further study, but there is at least like a parametric regime where it's actually like kind of interesting. And even up until 2048, you're sort of in this interesting regime. Yeah. So that's the sort of motivation here. If that makes sense here. And you can, you can study this. I haven't defined the Wishart yet. I've just defined a sort of rectangular, non-symmetric Gaussian distributed matrix. Maybe I could think about its singular values. Actually, what I'm going to end up doing is thinking exactly about its singular values, because there are sort of two matrices I can build out of this H that are symmetric. The first one is what I would call the empirical covariance. And I think the empirical covariance, just to remind myself, yeah, and H is again n by t. So right, okay, and t is the number of, yeah, okay. I just want to make sure. Yeah, okay. There's a sample covariance matrix and the covariance of the observation. So there's first H times H transpose, and because H is n by t, I should divide this by t to make sure it concentrates correctly. And I'll call this E. And then there's this F, which is equal to H transpose H divided by N, right? And this is sort of, this is my, F is more of like my estimate of the covariance matrix, because I'm sort of averaging over all the observations and calculating them. In either case, both of these have same non-zero spectrum.
In the scaling.
Sure. Say again?
In the scaling that you do.
Scaling, yeah. Modulo scaling up to factors of Q or Q inverse, if that makes sense. Right? I think that's right. I think that's like exactly precise. So more specifically, I would say TE is equal to NF in spectrum. Little non-rigorous, but I mean, that's exactly right. In non-zero spectrum, these are identical. And I can, because of this, I can relate, there's like a relation, I'll just like write it out. You can like relate their like Stilches transforms, like if you know GF, then you can automatically get GE, and it's not like super trivial, but it's like a one-line proof to show that you can like relate it to GE of Z by this like Q squared, and then there's plus 1 minus Q, and this it's easy to understand what this term does. This is exactly counting the zero eigenvalues, basically, the number of zero eigenvalues, because notice it's like Z minus 0 down here. So this is the zero eigs, and these are just like the non-zero eigs.
Sorry, so what's that 1 minus Q divided by?
Z.
Z.
These are all functions of Z. Yeah, these are all functions of Z.
Cool.
It's super clear here. Yeah. Right. So it's just like a quick thing you can do. I'm more interested sort of in understanding. So the point is, in either case, you can study, you can use similar arguments to ask what is sort of the P of H? What is that probability distribution? And you actually have to like, well, that's a Gaussian. That's a Gaussian, because we assumed that each of the HIJs are drawn from Gaussians. But then knowing that, you can ask, what is P of E? And this is actually a little bit less obvious. And it actually requires some serious like massaging of like the Jacobian. And you will get that like up to some constant, it looks like something like the determinant of E to some factor. So that's the actual Jacobian of the transformation that gets you E from H. There's like this factor of T minus N minus 1 over 2 times the exp of T over 2, I think minus T over 2, trace of E C inverse, something like that. Point is, it's like an exactly knowable thing. This is directly, you'll notice that this looks exactly like if E was just a number, this determinant just becomes something very basic. This thing becomes just a e to the negative x. This looks exactly like a gamma distribution in statistics, as you would expect, because that's exactly what it is. And T minus N maybe equals 1 or something like that. And you could similarly get an exact expression for P of F, whatever. I will, for simplicity, sort of study the case where the data is generated from white covariance. So if I set the true covariance of the data equal to 1, then simplify a little bit, and I can just define W to be a Wishart and W comes from something that is drawn from this P of W distribution that is proportional to, this. So I can rewrite it in a nice way. So it's proportional to this X of negative, watch this, negative N over 2 times this potential of W.
Mm-hmm.
And then the potential, this V of W.
So what's our W now?
W is, this is what I'll call, this is like, this is E when C is equal to 1. So this is a Wishart.
Oh, I see what you're saying. Okay. Mm-hmm.
Yeah, W for Wishart. I could have just written it as E. The book writes it as W. I'm going a little bit more on the book than I normally would, just for simplicity,
Sure.
and I don't
Just
want
to get
mess
it.
with anything. You can actually show that this potential looks like Q inverse W. That Q inverse is just to take the N to the T, plus this extra log term, 1 minus Q inverse log W.
Interesting.
Yeah. It's very interesting because now you actually, once I write it this way, you kind of have an intuition for what the matrix potential looks like. And the way that the matrix potential sort of looks like, and the sort of the sign of this term matters a lot, whether it's positive or negative, is you basically have, okay, the Q inverse gives you something that looks like a ramp, right?
Mm-hmm.
Asymptotically, like a linear ramp of the potential. And so I'm trying to draw this potential V of W.
Yeah.
Right? When Q is, I guess, greater than 1, which is exactly the under-parameterized classical statistics case, when Q is greater than 1, this potential term is positive. Is that right? Yeah, I think that's right. And I think you get something like that. Is that right? Okay. I think that's correct. I just want to check against a nice little drawing that they have. Yeah. So when Q is greater than 1, exactly. It's exactly this. I'll just write it a little bit better. So this is
just
maybe
drawing like a Gaussian with the yeah. It's like you interpolate between a Gaussian and a linear thing.
Yeah. And actually, it's actually weaker than a Gaussian. So because it's linear growth rather than, keep in mind V of like X for X a Wishart, sorry, for X Wigner.
Mm-hmm.
Basically like X squared. So the potential looks like this. So this is like long, heavier tails.
Yes.
Heavier tails. And then if I had for something like Q equals 2, and actually just let me make sure of one thing. So Q equals, I just want to make, sorry, this is Q equals 2. This is the underparameter. So right, this is Q equals 2.
Q equals 2, yeah.
And this is Q equals 1/2. This one.
Mm-hmm.
Very different behaviors around 0. So this is 0 right here.
Yeah.
And what does that mean? So in one case, I should probably point out that these are different graphs. So this is one case. This is the overparameterized. Yeah, and this is the underparameterized. Should be very explicit. So this one is under. This one is over param. I can like maybe delete the Wigner thing because we understand that. That's just, quadratic, whatever, simple quadratic potential. So these are the two differences. And it's a little interesting. So this is our potential. And I kind of want to understand. So this is Q equals 1/2. This is Q equals 2. And for Q equals 2, right, this is W, exactly. For Q equals 2, there's actually a sort of force of attraction that makes the eigenvalues want to fall to 0.
Mm-hmm.
And what you'll actually get at Q equals 2 is kind of interesting, is that you'll get something that's, so the distribution, rho of lambda of this thing for Q equals 2 will actually, so first of all, the eigenvalues are all positive because this is just a product of matrices. It's already different than the Wigner. It's not going to look like a semicircle, but it'll actually look like, for Q equals 2, a Dirac delta of weight, I think something like 1 minus Q inverse, something like that out here.
Okay.
And that's basically counting the extra 0 eigenvalues relative to the other matrix. And then you'll have a different, just a complete, like a gap, like a meaningful gap, and then something with some tail here that will also end up being compact. It's kind of surprising.
Interesting.
you can basically think about it as like, you haven't really talked about eigenvalue repulsion, but some number of the eigenvalues fill this lowest energy state. It's allowed, it has some capacity for those lowest eigenvalues. And then there's all of a sudden a repulsion of where the other ones can go, if that makes sense. In the other case, you kind of still get a gap, but there's nothing at zero here. Right, so there's just a meaningful gap. So what does this have to do with linear regression? I can actually give you like the answer in very sort of coarse terms. Now, there's a little bit of ambiguity because this W, keep in mind, is sort of the E matrix that I was calculating, which is like this n by n matrix. I guess the book chooses to focus on this. I actually think that F is kind of a more interesting matrix because F is sort of your empirical estimate of the covariance. And that empirical estimate of the covariance, you know, this H transpose H, which lives in R T by T. So you're actually trying to get, I think this is divided by N. You're actually like, C is approaching this. This is like a bad estimate of the covariance matrix. It's not even a bad estimate. It's the best estimate you can do, but it's not exactly the true covariance. So in the case when the covariance matrix is the identity, this will be like almost the identity, but it won't quite be the identity. There will be off-diagonal components, whatever. And you're calculating the spectral properties of this. Well, it turns out that when you actually do basic linear regression, and you ask like, I learn a beta hat, that's my estimator from the data. And I look at H beta hat, which is equal to my Y hat. You know, that defines my Y hat. That's my estimate. And I ask, what's the difference between Y and Y hat? That's like, what's the expectation value of the squared error between those two, right? Over training data sets. You get that there's like this thing called the bias variance decomposition, right? Bias. There's also irreducible error if your data is noisy, but let's assume that our data isn't noisy. You get something that's like bias squared plus variance. And you can like look this up, we can even like talk about it, but in any book on statistical learning, you can quite quickly derive that the variance of your estimator is directly related to the inverse of this dude. It's directly related to the inverse of your empirical covariance estimate, which kind of makes sense. Variance, you know. So
sure.
Doing H transpose H over N, I can call that maybe C hat is equal to this.
Yeah.
That implies that my variance of my estimator, of my generalization error, maybe, you know, variance of this, EG. So this whole thing is EG. Or maybe I should, let me not call it like the variance of the generalization error. It's the variance term in the generalization error. The generalization error actually becomes a pretty tightly concentrated thing, but it has this variance term. So it's actually the variance of my estimator Y hat driven by the small sample of the data. It's the small sample of the data that causes this variance in Y hat. This variance is proportional to just this inverse of the C hat matrix.
Okay.
That's all I wanted to say. And now as soon as I say this, something really interesting happens. And this is the reason that like classical statistics sort of starts to fall apart. So in this case, this was the, and when I was studying E rather than F, this was the underparameterized regime and this was the overparameterized regime. You'll just have to believe that, you know, when I switch E with F, it turns out that this is overparameterized.
Okay.
Overparam. So it's the overparameterized matrix that has all of a sudden like a bunch of zero eigenvalues and the underparameterized one doesn't. It does make sense because they sort of flip, like in the overparameterized setting, like if E has a bunch of extra zero eigenvectors, F won't, and vice versa. So when you flip the size of N versus the size of T, which Wishart distribution, both E and F have Wishart distributions, but which one has the delta spike flips? So now this is the overparameterized one, and this becomes the underparameterized one. And the coarsest estimate I could give you for things that would make this thing explode would just be, what is lambda min? Right, basically this thing will explode when lambda min goes to zero, which makes sense. Underparameterized regime, because of this gap, you're fine. And you'll actually see, so as long as your number of data points is greater than your dimensionality, you can prove that that implies that lambda min is greater than zero. I think you can even show that lambda min lambda min has like a very explicit equation. I think like it's something like 1 minus square root of q squared or something. So that's sort of like the you can show that like there's like a lambda plus or minus that bounds like the two sides of the Wigner distributions, and it's 1 plus or minus square root of q. And we could have showed that if we use the cavity method and we're careful, and it's the exact same type of derivation as the one we did for Bishart. But the point is that all of these densities are always between lambda minus and lambda plus. You can analytically estimate these perfectly. And it's only, notice that the only time that lambda plus has an issue is exactly when q is equal to 1. Or lambda minus then becomes equal to 0. And exactly at lambda equals 1, or lambda, exactly at q equals 1, when you plot the generalization error, and the generalization error, especially in the modern regime, but even in a lot of the regimes, is sort of driven by variance. If I just plot the variance, you will see that this is q equals 1. The variance just completely explodes and has an asymptote at q equals 1. Sorry, yeah.
I see.
Just completely explodes. And so classical statistics would say, oh, the variance, kind of rises, and, the further, the bias also decreases here. The bias actually continuously decreases, so that's fine regardless, because the bias is sort of like the more input dimensions you have, the less bias you have, because you can fit more complex functions, whatever.
Yes.
The bias is continually decreasing, but the variance increases and in fact spikes to infinity exactly when q is equal to 1. And so the thing on this, you can think of like this axis as sort of counting like the number of parameters t at fixed data sized. Right? So this is small n or small t, which is like small number of features. Like you've pruned your linear regression so you're not like overfitting. It's exactly the point of not using too many parameters, small parameters. And then there's this explosion. And now you might say, okay, that explosion just happens, and then there's nothing on the other side. But actually, if I were to animate for you what happens for this Marchenko posture, so this is underparameterized. So as I guess it's technically as I decrease q, because decrease q makes me more overparameterized. This gap starts to close, and then exactly equals 1, it hits the boundary, and there's that gap, right? But then something happens. Then you're in this regime all of a sudden. And the gap reopens again as I keep decreasing q and going more and more overparameterized. So it hits the boundary. The boundary collects.
This is the double descent story in some sense.
Yeah. The boundary collects that number of zeros, and then it jumps off. But now here's the thing you need to appreciate. In linear regression, you have to invert this covariance matrix. The moment you overparameterize, this matrix is not invertible. So what do? You can't do linear regression when that's not invertible, but it does have a pseudo inverse. And the pseudo inverse is super simple. What is the pseudo inverse? It's the exact same thing as this, but you just ignore all the 0 eigenvalues. That's by definition what the pseudo inverse does. And you just take this. And all of a sudden, because this, as long as you're doing a pseudo inverse, so as long as your, the technical term is, as long as your beta is equal to this H transpose H over T, I guess, depending on how you're doing it, times H of Y, as long as this inverse is like regularized by a lambda, and lambda approaches 0 from the positive side, you're going to do the pseudo inverse. And another way of thinking about it is you're basically starting, you can think of it as actually making sure that you learn the linear teacher through gradient descent. And so, you might have many possible solutions to this equation, because this is, again, like an affine space of solutions. But as soon as you start from the origin and learn it through gradient descent, you will actually be guaranteed to converge to the minimum L2 norm solution. This is the minimum L2 norm solution. So you're actually, by doing the pseudo inverse, you're biasing yourself to learning the minimum L2 norm solution, and you're also getting rid of these 0 eigenvalues. And then again, your generalization is actually just driven by this gap all over again. And this gap actually continues to increase as you get more and more overparameterized. And it drops down like this.
Nice.
So you can get this all from like the spectral statistics of the Wishart distribution.
That's really cool. Now, I just have a really short question, which is, if I just ran the same derivation for the spectral density, which we haven't discussed here, but at large n saddle
Yeah.
points, and then, start with the distribution over the matrices, do the Jacobian to transform into the eigenvalues, where I can, right, where I'm allowed to, and derive the distribution. Like, could I just do the same thing now, basically trying to do something like the chi-squared distribution over matrix entries, doing a Jacobian, and could I get to this distribution?
So let me just understand. So two things. First of all, we haven't gotten sadly to the joint distribution yet. So this Jacobian factor I mentioned here actually has nothing to do with the joint, and it's just
no, sure.
Sure. So you're asking, okay, you do this transform.
So if I just wanted to, like,
for scalars,
if I was just trying to get it real fast, right? Like the eigenvalue distribution.
Oh, okay.
And sort of like, if I wanted to know, so starting from, like, how would I derive the Wigner distribution, right? Over eigenvalues, I would just, like, you see what I'm saying, right? Like, I would just do the transformation to the eigenvalue basis, and then account for that through Jacobian, and then the Jacobian will give me the repulsion, and that's sort of why there's a difference in the first place.
So you're basically saying, we already wrote out this potential explicitly, and this is sort of getting to something that we haven't yet talked about. But you can absolutely write the joint density. And then what you would need to do is you would need to look at the equations of motion in that joint density. And the equations of motion actually give you your density, and it concentrates and gets large. And that is absolutely a way that you can get the joint density for this, both for the Wigner and for this distribution, which I don't know if I gave it its name, but it's the Marchenko-Pasteur distribution. And it's also very universal and important, very important in deep learning theory distribution.
Very cool. Okay.
Yeah, so you absolutely could do this from the perspective of the sort of joint density of eigenvalues in that potential. Yeah.
Exactly. So starting from the joint distribution. Yeah, exactly. Okay. Very good. And I would just start from, like, just like how I would for the Wigner story, I would start with the Gaussian distribution over matrix entries. Here I'd start with the chi-square distribution.
Exactly. And there is a duality, actually. There's a duality between, I think, like Q and Q inverse when you look at the Marchenko-Pasteur of E versus F. Like, if you flip E and F, I think Q and Q inverse flip, or something exactly like that flips. And then these G's are related by a duality. So there are a lot of people actually in deep learning theory talk about, like, this duality between number of data points and input dimension. And there is, and it does just come from the Marchenko-Pasteur, and it's not a deep duality. It's actually just, you can just reinterpret
no dualities no dualities are deep when you understand them at the level of function transformations.
Yeah, exactly.
The only deep ones are where we can't do that anymore.
Yeah. You can't do it in the first place. Like, exactly. Yeah, I mean, there are some beautiful, like, connections. There are, like, Coulomb gas analogies that we could talk about, but I think this is actually a pretty good place to cap it off, because we really, like, reached our sort of first result of why random matrix theory is important. And it really does give you a meaningful insight into this bias variance decomposition, because
definitely
the pseudo inverse biased us towards, like, the minimum L2 norm automatically. That is inherently a type of regularization. And a lot of signals, like a lot of true signals, actually do lie near the minimum L2 norm, and not just out here in, like, crazy high L2 norm space. Yeah.
Awesome.
So this is why over-parameterization kind of works in remarkable ways. Yeah.
Awesome. No, that was great. I didn't expect that we would hit this, but yeah, I guess we went from random matrices to double descent. Yeah.
Yeah, it's super impressive, I think. I'm proud. Double descent. Awesome. We did both Wigner, Marchenko-Pasteur, and yeah, I mean, anyone could sort of go through. I really want to stress that a lot of the motivation and the notation that we've been using here is like the Bouchard and Potter's book. Great book.
I'll put in the description. For sure.
Yeah. I want to give the credit they deserve, because yeah, definitely, like, a lot of the tricks and, like, the setup is coming from them. And a lot of these, like, deeper insights about free probability and crossing phenomena that happen both for, like, these Wigner ones, but also the Wishart matrices have, like, these interesting free structures. I think one thing that I would love to talk about if we had more time, or in another podcast maybe, is actually, it's good and well to understand how to, like, take these distributions of matrices and be able to calculate spectral statistics using tricks like replica method or cavity method. But there are now, like, a lot of advanced tools called the R transform and the S transform that allow you to, if you know the distributions of two random matrices and you multiply them together, you can create these things like the R transform, which is actually the equivalent of like the log partition function, which is additive under adding two systems together. It's the equivalent of the cumulant generating function for random matrices. And it satisfies this very nice property that you can now calculate these, the distributions and the resolvents of sums of random matrices. And then there's something called the S transform, which takes that even further, that you can now calculate spectral statistics of like arbitrary products of random matrices. And there's some very cool connections with quantum chaos there and things like that.
Yeah. Very cool. Well, I mean, there are a lot of cool connections that as we were discussing a little bit offline.
Super cool stuff.
Yeah. Well, thank you so much, Alex. Appreciate you coming on. And if you've made it this far, you got to subscribe, leave a like, and we'll return next week with another episode of Theoretically Podcasting.
Awesome. Cheers.